We all know what's a car, and we don't know is what actually makes that car. We see it from the exterior and say based on looks and performance, we say it's good, bad. But what we don't know is what actually it consists of, the various sensors that is there in an automobile. So the data exchange between numerous number of control devices, sensors and actors, they all are present in the automobile. Now, what it consists, what we don't know is there are various sensors that controls a lot of different actions in our car. So the various sensors act as an input to a controller. What I'm explaining is a functional block diagram. And the controllers in turn controls the actuators in the car. So just for an example, say a car wiper system, there are rain detection sensors, and there's a controller that controls, based on a software, it checks whether there's a rain or not, and when it does sense, the actuators actuate and the wiper moves. So it's a very brief overall introduction on what an automotive system is. Now coming to the vehicle bus. A vehicle bus is a specialized internal communication network that interconnects components inside a vehicle. Example, automobile, bus, industrial, agriculture vehicle, ship or aircraft. Now, we saw the various sensors that's there inside the automobile. How are all these connected? So there is a vehicle bus. There are various different types of vehicle buses which we will explain in the further slides. Now, the special requirements for vehicle control is assurance of message delivery, assured non-conflicting messages, assured time of delivery as well as low cost, and finally noise resilience and redundant routing. The different messaging protocols are control area network, linear integrated, sorry, that's a mistake there, it's local interconnect network, MOS FlexRay. And what we will be explaining in the further slides is basically LIN, CAN and FlexRay. MOS is for multimedia oriented applications controlling inside the car. So it's just an overall overview. The physical transmission media are single wire, fiber optic cable or twisted wire. Either any one of these can be used based on the protocol. So the kind of diagram to show the existing vehicular networks. As we see, LIN is the most cost effective and got a very low data rate. And there's another protocol J1850. I'm not very sure about the explanation for this, but I can look into the first slide and tell you. CAN, again, it's got a data rate of up to 1 megabit, and it's little much costlier than a LIN network. Computer FlexRay, higher data rate, and so on. Different protocols which are used in today's cars. Okay. Now coming to CAN. It's a controller area network. This protocol was it was developed by Bosch in 1983. It's the most widely used protocol in today's cars ever since it's been launched. It's been about 20 years and still running, and CAN is the most widely used control protocol. So it's got an ISO standard, ISO 11898 for serial communication, and it is primarily used as a high-speed CAN in the powertrain and chassis areas. Powertrain is basically the engine, anything to do with engine and power transmission, and the chassis areas is more like the structure, the the suspension, the steering, etc. And low speed CAN for the convenience area, for small applications like the engine wiper water, the wiper water tool. The transmission medium that's generally used is a CAN interface is made of two parts, the communication software part and a communication hardware part. And we'll go a little bit in detail on CAN. This is the overall network architecture of a CAN protocol. In the OSI layer, it takes the last two layers of the OSI layer, that is the data link layer and the physical layer. Now, the physical layer is the actual interconnection between the different CAN nodes, and the data link layer is where the communication is established. The controller will assure that there is a communication link between the two nodes. So as you see, it consists of a CAN controller, a CAN transceiver, and CAN bus, which again is the physical layer, which is connected to a CAN bus. CAN network is a system network made of CAN nodes. Each node has a host processor. The host processor dedicates what receive message mean and which message wants to transmit itself. The sensors, actuators and control devices can be connected to the host processor. Next is the CAN controller, the actual controller, the hardware with a synchronous clock. It takes into account the receiving and the transmitting. The CAN controller stores received bits serially from the bus until the entire message is available, which can then be fetched by the host processor, usually in the CAN controller, has a trigger and interrupt. Sending the host processor stores its transmit messages to a CAN controller, which transmits the bits serially. And finally, it's a transceiver that consists of a receiver and a transmitter. Now, receiving, what it does is it adapts signal levels from the bus to levels that the CAN controller expects and has protective circuitry that protects the CAN controller. Transmitting, it converts the transmit bit signal received from the CAN controller into a signal that is sent onto the bus. Now, a general message format. I didn't go to put the entire actual frame format of a CAN controller. So the general format consists of a header, a data bit, and error detection. Now, what the header consists is, it's basically an identifier. It's either 11-bit or an extended identifier of 20-bit header. Okay, it contains the global priority information, as in which message get into the bus first. We'll come to an example where we will see based on the global priority. Header often contains source, destination, and a message ID. The data is the actual data that's being transmitted. Application of high-level standard defined data fields. It's 0 to 8 bytes of data. And the error is used for error detection based on 15-bit CRC. Now coming to a general CAN operation in a bus. Now here you see there are two nodes, CAN node A, CAN node B, and this is the CAN bus. Now initially there is one frame already being transmitted, as you see, and next the CAN frame A wants to send data on the CAN bus. So what happens is, it sees that the CAN bus is busy and it cannot transmit unless and until this has finished transmitting, the CAN frame X. So it has to wait in queue. Now as you see, CAN node A, CAN frame A requested, now CAN frame B also requests during the same time when CAN frame X is transmitting. Now it also, as per the previous CAN node A, have to wait until this finished transmitting. Now what happens when the CAN frame X finishes transmitting? Now since CAN frame A consists in the header, the priority, the identifier identifies CAN frame A as a high priority data. The CAN frame A gets to transmit data first. Okay? And then CAN frame B have to wait until this CAN frame A finishes transmitting. Now, what if there's another frame during CAN frame A which is being transmitted, and that also has a high priority? So what happens is CAN frame B will further shift and it has to wait till the next higher priority data is being transmitted. So it keeps going on and CAN frame B have to keep waiting. And finally, when CAN frame A finishes transmitting, and CAN frame B can then transmit when the data bus is free. Now this is the basic CAN operation. Now coming to the CAN versions, there are different versions. One is a low speed CAN, high speed 1 Mbps CAN of 2 versions with an identifier bit of 11-bit and extended identifier bit of 29 bits. These are various versions that are available. Now coming to local interconnect network. Now since the 90s, after the 90s, when the applications increased, there were more and more devices or sensors that are being connected and using CAN bus in a automotive, in a car. So what happened? It started having a network overloading, and even small applications like low-cost sensors needed a higher cost CAN controller. So CAN was too expensive for connecting cost-effective sensors and actually in the convenience area. So hence, there was some OEMs joined together to form the LIN consortium, whose goal was to develop a uniform, standardized and cost-effective communication systems, so that it coexists with the CAN bus inside an automobile, but it takes care of the low sensor and the low cost sensor and low application area. So LIN consortium was founded by 5 automakers, that is the BMW, Volkswagen, Audi, Volvo Cars, Daimler Chrysler, with technology supplied obviously by Motorola and Volcano Automotive Group. Now LIN bus is a single master, multiple slave, and the master can also transmit messages to itself. So it consists of a single wire and a master is connected to each slave. Now a basic structure is given here, and the slave card consists of a microcontroller and a transceiver, which can transmit or receive data based on the master. So coming to the communication part of LIN. Now the LIN communication message frame, it consists of these certain fields. The break field, it tells the master will tell the slave that there is a message that is ready to be received. So when the slave receives a break field, it then there's a sync field where the slave synchronizes itself with the master's clock. Now after the slave synchronizes itself with the master's clock, the identifier field will tell the slave as in what data to expect. Now once the slave understands that, the data field is the communicated data that is being sent. And finally, the checksum. Checksum is to ensure that the data has been received correctly. Now, based on this, there are 2 types of data frames. One is the transmit frame and a response frame. So, the transmit frame and response frame, the break, sync and identifier is only set by the master in the LIN controller, and the data and checksum part, it can be set either by the master or the slave based on whether it is a transmitting or a receiving data. So that's the basic of CAN and LIN. Now the further on FlexRay, it will be explained by my colleague Mr. Sanjay.
Bonjour. Okay, my part is FlexRay. What is FlexRay? FlexRay is a next generation automotive network communication protocol. It is a much higher version of CAN.
When was it released? The first public release was on June 2004. The latest version is 3.0.1, which was released in October 2011. Okay, why we need to use FlexRay? CAN is totally event-driven and FlexRay is time-triggered approach. So the priority is eliminated and FlexRay is totally fault-tolerant. And many other advantages are high bandwidth, it is flexible, fault-tolerant, and reliability. The main importance of FlexRay was the formation of the FlexRay consortium. FlexRay consortium, a significant reason for this FlexRay was the foundation of FlexRay consortium under the guidance of 2 giants, that is Daimler and BMW, which they joined with 2 chip producers, Motorola and Philips, in the year 2000. Based on the byte flight system, originally which was developed by the BMW, the byte flight system was used initially in 2004 for airbags. The FlexRay consortium created the original equipment manufacturer independent and deterministic and fault tolerant FlexRay communication standard. So the main advantage was each member of the consortium can use it without having to pay license fees. The main fields of application are extremely safety critical and time critical automotive applications. And one more advantage is that FlexRay is dual channel and each channel can transmit up to 10 megabits per second. Today, the FlexRay consortium consists of 7 core partners, wherein BMW, Bosch, Daimler, Freescale, SK, General Motors, NXP Semiconductors, and Volkswagen. There are many other premium associate members and associate members who have joined the FlexRay consortium. This is again the core members who are in the FlexRay consortium. Implementation of FlexRay till now has been implemented in BMW X5 for suspension, BMW 5 Series, BMW 7 Series, Audi 8, Bentley, Rolls-Royce Ghost. The motivation for creating FlexRay. In a high-end car, there are almost up to 70 electronic control units exchanging about up to 2,500 signals, approximately. Commonly used protocols like CAN, LIN were not fault tolerant. That's the main reason why FlexRay was founded. Regarding the FlexRay static segment and dynamic segment, I'll be explaining it in the next slide. But the main concept behind FlexRay is TDMA. TDMA stands for Time Division Multiple Access. The various topologies that FlexRay support are point-to-point connection. In point-to-point connection, it means that one FlexRay node is connected to another FlexRay node through a single connection, wherein supposedly if there are two or more FlexRay nodes, then it is connected by a common node, that's the star node. This is the passive star topology. In line topology, each node is connected to a line through different tap lines. So that's line topology. And active star coupler. Each node is separated by a certain distance, so we use an active star coupler. That is an active star topology. TDMA. As I said, TDMA is time division multiple access. It is a time triggered approach. In TDMA, the frame is the whole communications cycle is divided into slots, and each slot is time triggered. I mean, there would be a scheduled time wherein at what time what frame should be transmitted. So that's TDMA. Okay, FlexRay nodes. In CAN, this approach is not followed. It's totally event driven. But in FlexRay nodes must conform to a precisely defined communication schedule, which assigns a specific time slot to each FlexRay message for communication cycle. That's what I said. This approach to message arbitration leads to a very deterministic networking scheme. So it's totally fault you can determine the next node that's going to transmit. So that's one more advantage. This is just a graphical representation of the TDMA concept, which consists of 4 nodes, A, B, C, D, which are assigned specific time slots. And in this, we can see that each node is transmitting 2 messages at a particular time. FlexRay hardware. How does it work? The FlexRay consists of dual channel, and it is totally fault tolerant, and it consists of a bus guardian. Next slide, please. Okay. Each node has a specific communication controller, a host, a power supply, and 2 bus drivers, one for each channel. The figure shows the logical connections of each element. The host is mainly responsible for the application of the system. The FlexRay protocol is mainly handled by the communication controller, wherein the bus driver is used to read and write data to the physical medium over which the data is transmitted. The communication controller will basically handle the framing of data and checking of received data to ensure it was uncorrupted before it is being passed to the host. The host and communication controller share information such as the control information and payload data from the host, wherein the communication controller relays status information and data received. The host interface to the bus allows it to change the operation of the bus driver as well as the read and error flags. The timing in a FlexRay is very, very important. The FlexRay communication cycle is divided into static segment, dynamic segment, and a network idle time. Network idle time is very important because it keeps the global view of time. A macro tick is nothing but the node's own internal clock or timer. For any static segment, it has specific number of slots, and each slot is of the same size, and it has same number of macro ticks which are of the same size, but the micro ticks totally vary with each node because of the variation of the frequency in the crystal oscillator. These are the various variations. In a flex array message, it's not a fixed thing that it should contain a static segment, a dynamic segment, a symbol window, and a network idle time. It has various variants wherein the main thing is the static segment with the network idle time. It can also have a static segment, a dynamic segment, and a network idle time. And also the various variants. A symbol window is quite important because it communicates, it sends symbols. Suppose a wake up symbol like that. A macro tick and micro tick, as I explained. A static communication segment which has fixed number of macro ticks, but the variation is with the micro ticks due to the frequency of the crystal oscillator. The length of the micro ticks varies. Static segment. It is made up of equally sized slots. Each slot is assigned uniquely to one node. One node can occupy many slots. This is just a graphical implementation. Here we can see that node 1 is assigned to static slot 1, node 2 is assigned to static slot 2. Node 3 is assigned to a random static slot, and also a dynamic segment. A dynamic segment in a flex array message is quite optional. A dynamic message is used, a dynamic segment is used only for asynchronous processes. Okay, this is the representation of a dynamic segment wherein we can see various slots assigned to the various nodes. The nodes have, each node has a separate message to transmit, and the main thing for a dynamic segment is supposedly if at all an event is driven for an if at all it says send the frame, then only the dynamic segment would send the frame. Here we can see an event is driven wherein node A from channel A. So a send request is for the dynamic message A4 leads to the transmission of this message in the 6th slot. So the dynamic message expands to the length of the node, and the others remain the same. Supposedly two nodes wants to transmit the message at the same time. Again here priority comes in the dynamic segment. It is time triggered, but it is priority driven. Here the priority is in 7th slot. 7th slot. So the message is C4. So C4 expands to the length of the node, and D3, which is the next, expands to the size of the node. Flex array frame format. It consists of a payload, a header, a payload, and a trailer. When compared to the CAN frame format, both standard format and extended format, it can be seen that the frame format of flex array is much larger. This is partly due to the error checking. The CRC bit rate is 24-bit here. The header section contains status information such as status bits, which are indicating if the frame is a null frame. That is, it contains no payload data, or if the frame should be used for clock synchronization. There are also bits to indicate the length of the payload transmitted and the cyclic redundancy bits, so the receiver can determine if the header was received correctly. The payload contains the data to be transmitted over the network. The payload may also be used to transmit more frame information as an option, and this would be indicated in the header of the frame. The payload length can vary from 0 to 254 bytes when compared to 0 to 8 in the CAN frame, and this is a significant improvement. The trailer section, as I said, it contains a 24-bit CRC that is calculated over the payload and the header sections.
This is used by the receiving node again to determine if the frame was received without any errors. This is an example of a communication cycle wherein 4 nodes A, B, C, D are communicating. This is the schedule table wherein it consists of a frame slot, it consists of a static or a dynamic, and it is also specified which is the sender and which is the receiver. Since it is deterministic in static segment, which is going to send and which is going to receive, it is already deterministic. So in this case, as we can see, ID 0x01, it's a static frame, and the frame node A is going to send and frame node B is going to be the receiver. So the first message 0x01 would be sent to frame node B. Secondly, ID 0x02, it is again static, but frame node B will be the sender and the receivers would be node C and D. So 0x02 would be received by C and D. Similarly, it happens with 0x04, wherein the sender is D and the receivers are C and A. Coming to the dynamic, supposedly there is an action saying send frame in the dynamic segment, then the dynamic segment would be transmitted. If at all there is no event driven with the dynamic segment, no message would be sent. The comparison between LIN, CAN and FlexRay. Coming to the application, LIN is used for low-level communication system. CAN is soft real-time systems. FlexRay is hard real-time system, X by wire, shear by wire, break by wire, etc. The control in LIN is basically a single master. In CAN it is multi-master, and in FlexRay also it is multi-master. The bus axis is in LIN is polling. In CAN it is CSMA. And FlexRay it is TDMA, FTDMA. Sorry, I didn't say about FTDMA. FTDMA is also similar to TDMA, but it stands for Flexible Time Division Multiple Axis. In FlexRay it is used in the dynamic segment. Bandwidth in LIN is 19.6 kilobits per second, and in CAN it is up to 500 kilobits per second. FlexRay it is 10 megabits per channel. Data bytes per frame, it is 0 to 8. In CAN it is again 0 to 8. In FlexRay it has an extended frame, so the number of bits is 0 to 254. Redundant channel, it is not supported in LIN or in CAN, but it is supported in FlexRay. Physical layer transmission is using a single wire. It's an electrical physical layer. It's a twisted pair in CAN, and it's optical and electrical. Regarding the application and an example, will be explained by
the FlexRay was first implemented in 2006, and as we saw, it was first BMW where they had implemented it, and the FlexRay controller was put in. It was used only for chassis. Then further, they developed FlexRay. In 2008, it came to the powertrain, which was the power and the engine part. And in the same year, it was developed as a high-speed CAN replacement. So wherever applications required a high-speed data rate, FlexRay was used. And finally, in same year, FlexRay is now a backbone in automotive systems where FlexRay protocol is being used. So further advancement is in applications is that in this year, in 2012, they are implementing the by-wire systems. Just as Sanjay said, the brake by wire or steer by wire, which is for your cruise control, or where your actual mechanical person will be replaced by an electrical, electromechanical. So that's the by-wire systems. Now, a FlexRay example, as I told, it was first used in BMW X5 in the chassis for the suspension control. So that's the FlexRay hardware, what you see, and that's the present scenario of FlexRay. And finally, a small summary. The FlexRay protocol developed by FlexRay Consortium has already found applications in automotive industry and looks set to become network scheme favored, especially in the X-by-wire. application are the safety critical systems. There is ongoing research into the migration from CAN to flex ray based systems, and as such protocol could find itself being used many areas, not just in the automotive industry. With this determinist pen triggered approach and high data rates achievable, it's also suitable for safety and control applications. So with this, we conclude our presentation. These are the references which we use. A few of them are listed here. And thank you.
Thank you. Question? You are very kind. Yes.
You said that the flex ray is fault tolerant. How different it is from CAN?
Yeah, in CAN it is totally event driven. It is based on priority. But in FlexRay it is totally deterministic. Like
So FlexRay is a 2-channel.
yeah, it is 2-channel, and moreover, in CAN it is only 1 megabits per second, and it is a single channel. But in FlexRay it is like it has 2 channels which can transmit up to 10 megabits per second. And
Even if there is a fault, there is one channel which
And
can
mainly
go over.
it is the 24-bit CRC that takes care of the fault tolerance.
Thank you.
The time slot in X-ray, the duration, is it fixed? Is it variable? Who decide of the duration, of the number of slots, and so on?
The time slot it is fixed. The length of the time slot in a static segment is fixed, but in dynamic segment it might vary. In dynamic segment there is something called as the mini slot. In the static slot, the slots are further expanded to macro tick and micro tick. The macro tick again it is fixed. It keeps it's the internal timer of the of the clock. And micro tick it is varying because mainly due to the change in frequency of the oscillator. So
Who fixes that time slot? As we understand.
it depends on
I
the
think by some
length of the
controller.
static slot.
Not
Yes, my question is,
Yes.
in all systems which use FlexRay, is the time slot always the same? Or is the time slot fixed by a configuration or something like that by developers when they decide the
Yeah, I'm not very
application?
sure, but as I understand, I think the different manufacturers will have their own fixed time slot based on the
Depending upon the application.
I'm not very clear about it.
During a static time slot,
Starting,
Yes.
which is associated to a specific node,
Yes.
is the node obliged to send a message during the time slot, or could the node doesn't send nothing?
Okay.
Yes, sir. In that case, since it is dual channel, supposedly we take an example wherein node A and node B wants to transmit, and node B doesn't want to transmit. So the second channel would be used as for increasing the data rate of the first.
I'm not sure it's answer to my question. My question was, do a time slot can stay empty? For a static, a dynamic, you say that
Yes.
maybe
Yes. No, sir.
we could have no transmission during a dynamic
Static is totally deterministic, as in what will be transmitting next. So according to the schedule table, whatever is fixed or whatever is done, that would be transmitted.
The nodes which are ready to transmit and those are scheduled already in a
Suppose
scheduled
node A transmits a message, it would have a specific time. After that specific time, another slot would be assigned for it to transmit a message.
Yes, but in this case, is it detected as an error in the system or not? An empty static slot, is it an error or is it normal in the system? There is two, I don't remember the name. You can go back. Two channels of transmission. Do these channels work always together by sending the same data at the same times to assure integrity of transmission?
Yes.
Or could they send different data each one?
It can send different data. Because when one channel is already but then how is that? Because fault tolerance it uses one channel.
I think there is an hesitation. Okay, so another question.
Yeah, what is the future of FlexRay?
Huh?
Future.
High-end applications like
FlexRay right now CAN is the main backbone of automotive systems, like for all the controlling. But CAN is limited to a 1 megabit data rate. So now there are more and more technologies advancing where you need faster data rates. And FlexRay is that which has got a higher data rate, and it is not, it's not very cost effective compared to CAN, but it can complement along with CAN. But FlexRay's application based on the development today, based on say how fast data rates we require in today's world. So that's where FlexRay comes into picture. And higher end means higher use. So that's it. And not just automobile. It's going to be used, or it's actually in fact looking at like suppose say buildings and for automation and stuff. So that's where agriculture.
Thank you.
Okay. Thank you.